It is not clear. Huh? Where?
Rajendran sir, kindly mute yourself. Good morning, Dr. Vishnu.
Hello, good morning.
Good morning. We have students from grades 9 to 12 with us today. So we will start the session.
Sure, great. Thank you so much for organizing this, and I look forward to interacting with you all.
Yeah, our pleasure. Thank you. So before we start the session, good morning, children. Good morning, resource person, Dr. Vishnu Viswanathan. Children, I've conveyed to you, today we are going to have an informative webinar on educational opportunities in lunar science. And it gives me immense pleasure to introduce our resource person, Dr. Vishnu Viswanathan. He is a research scientist at NASA's Goddard Space Flight Center. He is an expert in the high precision modeling of lunar and planetary orbits and rotation, and uses various tracking data like laser, radio, images, and their derivatives to optimize these models. He has also led several NASA research and development projects as principal investigator and is currently involved in interagency activities related to defining reference systems on the moon. So today he will be sharing an overview about his work related to moon and how you can learn more from him. Over to you, Doctor.
All right. Let me just quickly share my screen.
I'll give you right. Yes.
Okay. Yes. Can you see my screen?
Yes.
All right. Okay. Okay. So again, thanks so much for organizing this and giving me the opportunity to talk to you all. And I'll save some time towards the end for questions, so you can raise your hands and come forward and unmute, and then you can ask questions. So today what am I here for, right? It's I think one of the things that I really want is to really bring down um, uh, how we view scientists. We often view scientists on a pedestal. So I want to bring that down and be able to communicate to you all in a way that hopefully you can understand. And I'll save some time for Q&A for that. But to bridge that gap, because when I was on your side, I was also a student studying in one of the Indian schools in Oman back 17 years ago. And I took a very roundabout way to reach where I am. Okay. And the students are not usually fully aware of the different available career paths to enter into the field of space sciences, because again, we think of space science as a field that is very unreachable. We talk about them as rocket scientists, and it just makes us mentally unreachable. So I want to tell you, that's not the case. What I believe in is that you can it goes down to the basic fundamentals of sciences like physics, math, and what I believe in is that you can also understand it and learn it, because it's a very intuitive field of space sciences. So today I'm really here to bridge that gap. Okay. So I'll tell you a bit about my line of work at NASA. So I'm a research scientist there, and I've been working there for almost now 5 years, 5 years and plus. And what I enjoy doing is this field of study called planetary geodesy. So it's a field of science where we measure like a planetary bodies, different properties, uh, like the gravity field of it, which is essentially how um, mass is distributed on a planetary body surface, which by that I mean, how the mountains are, how much mass the mountains are, how much, how the weight is distributed across its surface, um, and how we can measure it, right? So there's gravity, there is topography as well, which is, I'm hearing an echo. Um, so there's topography, which is essentially a way of measuring the mountains and valleys, its heights and depths. Also, there is rotation. Rotation tells us a lot about how a body's interior is, and I'll give you some nice examples and kind of guide you through the way. So I have a question for you, and what I'm not expecting an answer, but I want you to think more on how we can measure gravity, or how can we measure how the mass is laid on different parts of a planetary body, right? Think of when I say gravity field, it is really, excessive mass in certain areas. So more mass means, if you are going to fly above it, you will get a slightly stronger pull, right? Because there is more mass, and we know that the force is acting on, if I'm flying across a mountain on above it, I should feel a very small greater force, because force is proportional to mass times the acceleration, right? um, and so this is exactly how we measure it. So I can show you a nice, let me see. Yes. So what you're seeing here are two spacecrafts which are flying across the moon surface. And the mission is called the Grail mission. Okay, it's an acronym. We like to use a lot of acronyms at NASA, and the acronym stands for Gravity Recovery and Interior Laboratory. Okay, it's a mission. It's a what is known as a twin spacecraft mission. So two satellites, um, which is used to map the moon's mass distribution. So that's what gravity is, right? So now think of it like a vehicle going above, let's say, a speed bump, right? So the force that you feel when you go above a speed bump, you'll feel it on the front two wheels first. So exactly in that scenario here, you'll feel the force on the first satellite that's going above it, the satellite in front, depending on the direction. And you'll feel kind of the similar force, which is felt by the wheel behind, right? When you're going above a speed bump. And so now that's exactly what we do for this mission. We are measuring how tiny forces act on these spacecrafts, and we are also tracking these two spacecrafts. So I hope you can see the video. And so we let these two spacecraft talk to each other, and at above a certain height, and we fly across the moon, and we do that until we map each and every part of the moon. Now the trick is you will have forces acting on it from other sources, right? So the gravitational pull acting from the Earth, the gravitational pull acting from the sun, the small changes acting on these spacecrafts coming from just, the solar radiation pressure, it's called, because they tend to affect it so minutely that they are sensitive. So if you consider all those other effects, what you're left with is the gravity field of the planet about which they are orbiting. So this is how we map how the mountains and valleys are and the mass is distributed across them. And if you were to plot on a globe how that would look like, this is how it is. So what you're seeing is the near side of the moon, just like we see it. And the color is coded. So, this is not the exact color, but that we see, but this is the color that we put in to indicate how the mass is varying across its surface. So, for example, what you see in yellow is mostly flat lands. It's very close to zero, changes in gravity. Whereas the red is mass excess, which means there is more mass there. And in the blues and the greens that you see, it's mostly valleys, or like there are some mass deficits, as we call it. And we call this a term known as free air gravity. Okay. Now, why do we do this, right? Why should we understand how the mass is distributed? The very interesting thing about the moon is that since the moon does not have all this atmosphere and rivers and water like we have on Earth, changes on the moon surface, let's say that if there's an impact, right? If there's an asteroid coming and hitting the moon and then makes this splash, and that's why you see these round features. So when that happens, it gets preserved because there is nothing changing it as much as we know things change on Earth, because rivers carry over sediments, and the atmosphere facilitates changes, and there's rain, and there's so much of things that goes on Earth. But on the moon, moon does not have an atmosphere which is dense enough like the Earth, and so there's very less mass transport, as we call it, which is just changes in mass, right? Because so what happens is that over billions of years, what we are seeing on the moon surface, you can track them back to billions of years ago. And that tells us a lot about how the moon formed, how it evolved as a function of time. And yeah, that's how we map gravity of different planets. Isn't that cool? So I'll show you how it looks like also on the behind. And that's very interesting because you can see all these beautiful changes. You can see those reds really pop out, mostly on the far side of the moon. And really the Grail mission, without the Grail mission, it was almost impossible to map the far side of the moon, because most when we are trying to map how the moon, how the mass is on the far side of the moon, we are unable to track those satellites because there is just because it's behind, right? It's and the moon is facing us at all times in the same way. So Grail was able to do that because the architecture of that mission was different. Previously, we were tracking just one satellite, and so we would lose connection when it goes behind the moon. But with this twin satellite setup, you can have satellites which are talking to each other, even as we lose connection with Earth, and we get that data back once it comes around. So that's really how we map gravity field, and we have mapped that for different planets in this similar manner. If you think of it, it's the way gravity acts on different parts of the changes in that motion of that spacecraft is really what enables us to track these changes in gravity. So we saw gravity. Now think about how we would measure topography, which is just a fancy term, which just means, the different mountains and valleys. We're going to measure height, right? Before with gravity, we measured what's the mass under them. But with topography, you're going to measure how that, the different heights changes as we go across the moon's surface. And the best way, well, on Earth, if you want to measure small distances, you can use a ruler, you can use, a tape, but think about very long distances, right? We really can't do that on the moon, especially without, human presence there. And so instead, what we do is we use lasers, because lasers can tell us how much time did, a pulse of laser take for it to go from, let's say, a satellite to the surface of the moon, and then bounce back and then capture it again by the satellite. We know the distance, well, we know the time taken, right, between those two pulses as it bounces back. And we know how much time, speed of, we know the speed of light. So we can compute what the distance is. And so we sent a spacecraft, which is actually even currently orbiting the moon. It is known as the LRO mission. That's what the logo you see on the right. It stands for Lunar Reconnaissance Orbiter. So it has different instruments on it. And one of the instruments is known as the Lunar Orbiter Laser Altimeter. So it's the acronym for it is known as LOLA, LOLA. Okay. Again, we like acronyms. And so you can see how that would look like. So this is that satellite. It bounces pulses on the moon surface, laser pulses, and depending on if it would hit a mountain or if it would hit a valley, the time taken by that pulse to come back changes, right? And that's the principle that we use. Very basic principle. And let's say we put that again, just like how we map gravity field. Let's map how that topography or that mountains and valleys look like on the moon surface. So here the color scale is slightly different. So the greens are close to the greens are basically the flat surfaces. The small tinges of blue are more like valleys, and the yellows and the reds are mountains. Okay. And let's give it a spin. And look at how the far side is very different as compared to the near side, right? So that was the far side you saw in yellow and red. And on the near side, what you see is mostly flat, mostly flat lands. And the reason for this is there was a lot of volcanism on the moon surface back, several billion years ago. And what happened was it, kind of flattened out those regions that you see, even though those are areas where those round circles that you see in the front, they're all areas where there were impact that happened. And so you would expect, there's some depression in the surface there, but, there was also volcanism that filled up all those, they're known as basins or impact craters, those regions. So is that cool? So I'll show you the far side of the moon. And it's all these highlands. They are known as the highlands because they're just more thicker crust on the far side as compared to the near side, and much more older is what we know. So you saw gravity, you saw topography. Now I'll get into something that's more interesting, which It's my personal favorite. It is the rotation. Okay, this is the exact color that we see of the moon. Now I've written here phases of the moon, but what I want you to look at as the phase changes, I want you to look at how the moon wobbles. So you will see a slight nodding motion of the moon as it goes in its orbit. So there's this front and back motion, right? Because the moon's orbit around the Earth is not exactly circular. There is a small, it's slightly elliptical. So as you may know, eccentricity is what makes it slightly elliptical, right? So there's a small eccentricity value, which gives you that front and back motion. But I also want you to look at the nodding motion, which is like up and down, and also side, like left to right, right? That's called the, what we call it is librations. So these are the longitude librations for the top to down nodding motion, and the latitude librations. So these are very small changes from a uniform rotation. And there is a reason why this happens. Okay. And I want you to, the way I help somebody think of what that means is, so if you look at this slide here, so this was a very fun experiment by Donald Pettit on the International Space Station. So what he took up there are two egg-like decoys. Why decoys? Because they don't let you take real eggs into space, or at least the International Space Station. So these are like toy-like decoys, which look like eggs, and you can see how. So what I've done is that I've marked A and B. These are going to be the end points of each of those. So he's going to rotate them and spin it, and it's going to reach, the different points. So what I want you to do is look very closely at these two decoys. So this first one is A, and the second one is B. Okay. So look at how A rotates in space, and look at also how B rotates in space. So the difference between the two, now there's a question coming for you, okay? And it's okay if you get it wrong. It's just a way to help you think. One of them, it contains a fluid, and which means that it's filled with some sort of liquid, and the other one has a solid interior. So there's no sloshing of materials going on in the other one. So one is fluid and the other one is solid interior. So the question is, which of the two egg-like decoys it's containing a fluid? Okay. So I'm going to ask, who among you thinks that B contains a fluid? Please raise your hand up.
You just answer. Who thinks B contains fluid? Raise hand.
Okay, I see some hands. That is the right answer. And the reason for that is because, when a solid structure spins, there is no change in the mass that is being inside, right? Whereas when a fluid structure spins, it's more chaotic. There's a lot of sloshing going on inside it. And so, it has a very peculiar different rotation as compared to a solid. Okay. And this is exactly how we understand the interior of the moon. Whether you believe it or not, this is really how we know the interior of the moon. Whether is it a liquid inside, By liquid inside, I mean, obviously we know that it has a solid structure outside, which is the crust and the mantle. But the question is the fluid core of the moon liquid or is it a solid, right? And so it's kind of difficult to understand that by eye, by just looking at the moon, because the variation is not as rapid as those spinning decoys that you saw. But we can track different points on the moon surface over a very long time. And this helps us to then build models which can then understand the rotation of the moon in a very fine manner. And so for this, we use a technique known as the lunar laser ranging experiment. Okay. It was funny because it was there was I'm not sure how many of you have probably seen Big Bang Theory, but one of the episodes, they go back, the crew goes to the top of the building terrace and fire some lasers and then get some measurements. Um, Although the principle is is good and scientifically accurate, you really can't do that using you need really powerful lasers for that. Okay. And you also need a telescope. And so this is exactly what we do. We have these different observatories on the moon, on the Earth's surface, so that those are the regions that you see on the top left corner. Those which are marked in red, there are all these different stations on the moon, on the Earth's surface, where we have these observatories with telescopes, and what we do is we fire laser pulses through those telescopes, pointing towards the certain mirrors that we have placed on the moon's near side surface. So these mirrors are kind of special mirrors. They are known as retroreflectors. Okay. The property of a retroreflector is essentially that when you shine any light onto a retroreflector, you get back the light in the same direction. All right. And the benefit of that is that when we fire laser pulses to those reflectors, we get them back to those observatories on the Earth. We know the time of laser pulses, and with the help of some of these models, we can predict how much time it took. We are basically tracking those reflector points on the surface of. So we have 3 set of reflectors coming from the Apollo mission. This is back 1969, 1970 time, and we continue to they work because they don't need any power. They just kind of mirrors the placed on the moon surface pointing towards the Earth, and so we continue to range to them using laser pulses. Isn't that cool? We shoot laser pulses to the moon to understand what's in the interior of the moon. And so we have got a lot of science from this data, and by trying to understand this data over 5 decades, 50 years of data, we have been trying to understand, very finely track moon's orbit in its as it goes around the Earth. Okay. And this is what it looks like. This is just a beautiful visual for you to really absorb. You can see that laser pulse in this particular case is shooting that they're trying to bounce that laser pulse to the A15 reflector, which is the Apollo 15 mission. You must have heard about it. It's one of those missions where we also had astronauts go there. They place these reflectors and point them to the Earth. And the beautiful red hue that you see is because it just happened to be a lunar eclipse, and so this is the sunlight passing through the Earth's atmosphere and then casting that beautiful orange red hue on the moon surface. Yes. So how accurate? So this is a question. I want you to, I mean, I'm not expecting an answer, but I want you to think how accurately we might know that distance, right? Is it at the level of a kilometer? Like how well is it? Because the distance to the Earth uh, from those observatories to the moon is at the level, the distance is something like 380,000 kilometers. So how well are we measuring that distance? Is it at the range of kilometers? Is it at the range of meters? Is it at the range of few centimeters? So I want you to think of that, okay? I'll give you a moment because these are, massive distances, right? The distance to the moon. And we're using really high power lasers for that. So the answer is 7 millimeters. That's incredibly small. That's incredibly accurate. So we are able to measure the distance to the moon and back at the level of 7 millimeters. So, and we're trying to go even lower. We're trying to put new reflectors on the moon, and we're trying to see, how well we can accurately track in order to better understand what's inside the moon, how the moon rotates, and we have a lot of mysteries that we really still are unresolved. And yeah, so that's the takeaway here. And we also, NASA is planning these Artemis missions, right? So they're known as, why Artemis? It's the twin sister of Apollo. So, we try to keep the heritage alive. And so Artemis mission, it's a series of missions, and now we're heading to the south pole of the moon. And the south pole of the moon is a very tricky area because you see all those different shadows. The thing is, on the moon's surface, we don't have power, right? We rely on solar power most of the time, and it's also very expensive to take equipments up there. So we want to rely on solar power as much as possible. And so you'll see all these shadows, how they change, right? It's very tricky because the sun does not go very high up in the sky for too long in those South Pole regions. They're just like, just a few degrees up. Imagine the sun going only till where, when the sunset happens, just a few degrees above, and then it goes back down again, right? So we don't have a lot of power coming from sunlight. And so it's a very challenging area for astronauts to explore that region. And what you see are these different highlighted regions. These are known as the candidate sites, where scientists are trying to understand and evaluate, where would be, where could we go and get samples of the rocks, etc., from, so as to get maximum science out of it. So we have to choose among different sites, and they have narrowed themselves down to about 13 candidate sites, which are what you're seeing here. They haven't made a selection yet, but stay tuned. Now, I understand that much of what I discussed today, it may be really new and exciting for you, but this is just an overview what you saw of the field of planetary geodesy, right? Now, this field is of great interest to space agencies because of the knowledge that we gain just by mapping or understanding where all these bits and pieces are of the moon, using gravity, topography, etc. And today what you saw is for the moon, how we do that. However, what I've noticed is, again, there is a significant lack of like educational material in this field that are suited for like high school students, because this is uh, now, why high school students, right? This is because this is the time where you make career decisions. like you're choosing science stream, or after your 12th, you're going to a different set of fields, and these are the decisions that you're making. And so I want you to be well informed of what is out there, what are the things that you can learn, and they're not very hard to reach. And so to bridge that gap, I will be offering a course which will be starting this October, where you can learn to take really like real data from NASA's data archives and websites, and do some exciting like hands-on coding, and really understand in depth how we do science at NASA, right? And so for those who are interested, you're welcome to sign up on my website. You can take it down if you need, and if you're interested. And there is a wait list, because I do get a lot of interest on these. And I'm really happy to also pass on maybe a flyer with all these information, to the principal and vice principal. Yeah, with that, I am happy to take questions. I think you can raise your hands, and then I believe your class teachers will help facilitate the Q&A here. So I hope you enjoyed the talk.
Yes, yes, very much, Dr. Vishnu. And we have our inquisitive learners who would like to interact with you. They would like to pose some questions to you. So,
Just sit there and ask. There's one student from 10B to ask a question. Yeah, please.
Good morning, sir. My name is Akshara Dubey, and I'm interested in aerospace engineering. But I want to know if I can apply my skills to lunar science research. Can I still pursue a career in lunar science if I'm not a scientist or astronomer? Are there any opportunities for engineers in the field of lunar science?
Yes, very much. Yes, to answer you very shortly, the answer is yes. Like for example, the one of the I'm just going to give you an example, and you can look up things. And so if you see this particular slide here, you did see that we need to be able to track those spacecrafts very, very accurately, because if we don't know where the spacecrafts are, we cannot do all these interesting science, and we cannot collect all that interesting data from these missions. So one of the work that is done by NASA engineers is to try and model the orbit of these spacecrafts. Which, what I mean by that is, how does the motion of that particular satellite vary as it goes around the moon's surface, right? So the field of one of the facilities that does this at NASA, and specifically NASA Goddard Space Flight Center, where I am from, is called the Flight Dynamics Facility. So here we track those spacecrafts using these really humongous dish antennas, which is known as a deep space network. And we try to model those orbits as this is one of the work done by aerospace engineers. If you're interested more in it, I would encourage you to look more information about this term known as orbit determination, right? Which is trying to model how that orbit would change. So orbit determination is the key word that you really want to look at.
Okay, sir.
And
Thank you.
thanks for your question. Yeah.
Sir, I had a question. Tell your name. My name is Aditya. I've heard that this is a pretty competitive field. Can you talk about some of the specific challenges that early career researchers face, and what advice would you like to give to someone like me who is just dreaming about it?
Yeah, that's a great question, Aditya. I think my general advice is that don't be afraid. Don't be afraid of the competition, because no matter what field you go into, you will face competition. Okay. And I think it's a very healthy way of, think of it as a healthy way of a measure of how much of hard work you're willing to put into this, how much of difficulties are you um, do you intend on enduring in order to do what you love or learn what you love. Okay. Don't see it as competition, as a hurdle, but try to develop um, perseverance, that grit, that never give up attitude, and then you will see that you can really cut through competition much more um, easily, because it's a mindset issue, I feel. But I agree, there's competition, but what we look out for are students who are willing to do what it takes.
Thank you, sir.
You're welcome.
So I'm interested in the future of lunar science. So as of now, it's developed, but not yet. So what are some potential breakthroughs or innovations that could happen in the next few years, and what's its impact?
I'm sorry, could you repeat that question, and also please mention your name?
Sir, I'm Arish Ajay. I'm, I want to know more of lunar science and what are some potential breakthroughs or innovations that could happen in the next few years, and how would it impact space exploration?
Well, just like any field, we build upon the knowledge that we have gained, right? But we have to start somewhere, right? So we are going to use all the knowledge that we have gained from Apollo missions, and really test new possibilities in terms of, if we are thinking about going to the moon, can we make it to Mars? What are the challenges that we would face if we try to explore Mars? We know that one of the examples I gave during my talk is, we know there's a power issue, which means that the lunar nights are very long. So what does it take to build instruments, scientific instruments, transportation systems, like rovers, etc., to really survive the night? And so there's a lot of problems that are still yet to be solved. And we keep building, we take those lessons learned, and we innovate. So yeah, it's a very incremental process.
Yes,
Sir, my name is Sainaba Satta. So in the 90s, 1980s, 1970s, there were many moon landings with humans. So why has there been nearly a 50-year gap since the last moon landing by humans?
Fantastic question. So thanks so much for that. This is the question we scientists ask as well. What motivated us to go then versus what motivates us to go now? And I think this is the real mindset, and mindset change, I must say. It took us a very long time to explore the moon, based on science, rather than based on a chase, based on Cold War, right? This is the space, which is really the Cold War is really what fueled space exploration. back in that time, because there was a chase to have some sort of superiority between countries. And the way things were done back then is to compete and show that, hey, we have reached the moon. But now things are very different. We are asking the right questions right now. Why do we want to explore the moon? What scientific value does it give us, right? We are not doing it as a solo country. We have the Artemis Accord, which is, it's a treaty between different nations. We want to go back to the moon as a community, as a species, as humanity, right? So it's really the difference in how we think that has taken us so long, unfortunately. So fantastic question. Keep asking those, we need them.
Thank you, sir.
Good morning, sir.
Yeah.
So my name is Ria, and I had my question. My question was that since you're a research scientist, as a research scientist, what do you do? What's your job? What all do you research about?
This is what I showed you today, is what I research about, right? So like let's say, I take a typical day in my office is me reading through different scientific papers. I have some major goals that I want to achieve for the end of the day. So I have, let's say, I want to be able to write some proposals, which are it's a way of keeping us funded, right? And we ask interesting questions. We do some preliminary studies. We say that, hey, this is a very important question that we want to understand, and we think that it's a way of asking for funds to scientists to help fund these studies, right? So we want to say that, hey, let's say we want to develop, let's say, an independent model of the moon's interior, right? So now the thing is, what does it take to build that? Can we analyze existing data? Is the existing data accurate enough? Do we have enough information coming from it? What are the remaining questions that we as a community, as scientists, don't know yet with that data? So what is a new set of instruments that we should develop in order to make new measurements and more accurate measurements? And what will it tell us? How will it fill us? How will it answer some of those missing gaps in the knowledge that we have? And so this is how scientists work, right? So we try to look for answers. We try to understand what the current knowledge is, and we're trying to really push that boundaries of knowledge. It's maybe small bumps, but we're trying to push it.
Thank you, sir. And sir, I have another doubt.
Sure.
A very interesting doubt.
You say your name, and then
My name is Gauri. I'm from 9B, and so we know so much about the moon, right? We know a lot of things about the moon. So, is it possible to make a second moon, like when the moon disappears, like when the moon disappears, then we can make a second moon, right? With all the things we have, like AI and all, we can make a second moon.
Well, that's a fun question, but it's not as easy as you think. First of all, you would have to tell me how we will potentially lose our current moon. Okay. Let's say, we do know that the moon, I mean, there is some basis in your question, which is, how can we lose our current moon, right? Now there is, all the oceans on the Earth. So the oceans on the Earth, all that sloshing that you see on the shores, there's also sloshing going on in the deep interior, which means, much more lower depths. So what happens is that energy that gets dissipated, the energy lost in the Earth's rotation, because of all this ocean sloshing, the moon has to kind of recede away, which means go slightly outward to compensate for that lost energy. Okay. So, but there will be a time where it will be in a very stable orbit and it no longer recedes away. Okay. Now, how do I know this? Because, I measure the moon's distance using lasers. So you can see how that moon recession happens. That's the first part of your question.
Okay, sir.
The second part, building another moon, there is significant, I would say it's a technological challenge than a scientific challenge. You need to, first of all, find all the mass that you can, put it together, which is, not an easy thing, and then get to orbit the Earth. It's a challenging endeavor, but it's a food for thought. Yeah.
Okay, sir.
Sir, I have a question, sir. My name is Rehan Sharan.
Sure.
So it has been 60 years since the first man on moon, Neil Armstrong, has stepped on the moon. How do you feel about the conspiracies of the moon landing, telling that like it's fake?
Well, the data, just to correct, it's been more than 50 years, right? It's 1969 is when, sometime in July, I think, when they landed. Well, the science that I do, so if you have to, there is no way to get back laser pulses when you shoot lasers to those specific points where we kept those retro reflectors if they weren't a moon landing. Okay. There is no other way you can physically or scientifically possible to get back those returns. You need very precise instruments, and you need them to be tilted exactly to be facing the Earth. And that's a proof. That's one of the many proofs to contest that. So if somebody tells you, oh, the moon landing didn't really happen, then you know what to tell them. You can just tell them, we fire lasers to them, we fire laser pulses to the retroreflectors, and we get back photons back, and there's no other way scientifically possible. And you can quote me on that.
Thank you,
So
sir.
this from
Uh,
12.
I have a question.
I think,
Yeah.
the person from 12A, please go ahead. Yeah.
I'm Kirtana from 12th. I'm excited about the prospect of working on lunar missions, but I'm not sure if I should work for a government agency or a private company. Are there companies that work on lunar research and development, and what are their roles? Can you also talk about the opportunities and challenges of working in a private sector versus a government agency?
Yeah, sure. I will try. So I haven't really worked in a private sector, but I can tell you something about government agencies, right? So like I think one of the questions was, it's a competitive field, so definitely there is competition. So that's one of the things to enter the field. But you also know how to get there, because I mentioned you can persevere and get through if you train yourself well enough, and if your skills are some of those things that are needed by those agencies, right? So in government sector, mostly what we like to do, and it varies across different space agencies. I can tell you a bit about NASA, and they fund activities which are mostly related to understanding the science aspects, right? So there's a lot of push to bring enthusiasts in this field to do more science, because there's a shortage of scientists in this field. If whether you may not believe it or not, it's actually true. We don't have sufficient scientists in the US working on these kind of things. It's so training the next generation of workforce is, one of the things that there is a focus on, and mainly because it takes time to train scientists, and post training we want them to continue to work in that field, right? So they take some training and then they leave. Doesn't really help science, or it doesn't help them. So what I'm trying to do here is trying to train and kind of influence your career decisions, so that maybe 10, 15, 20 years from now, I get emails from some of you saying that, hey, I've trained so much in this field, I've got all these experiences, and I think they will be suited to the missions that we are doing, and then I can just embrace the next generation to help them do the science. So that's mainly in the government sector. This is how things work, right? It's whereas in the private sector, there is there's one additional thing in the government sector, which is it's challenging to recruit foreign nationals, right? Because security issues are a concern across all space agencies, to be honest, and so it's easier when you're in the country, you've worked on something, and then you can gradually build your profile, and then be of interest, and hopefully in that time you have dealt with all the immigration and things like that. Whereas in the private sector, it's obviously there is capital involved. It has to be profitable. And so much of the work that is done in the private industry, it's mostly engineering work. So you don't see as much as science. So science is mostly for government and even universities. So, you can fold in also private universities, public universities, educational institutions, and research institutions for that matter. Whereas the private industry would be mostly delivering that spacecraft or making that instrument using the specifications given by scientists, because we know what to measure. They will help tell us how to build some instrument to be able to measure that thing. So yeah, this is the very broad difference. I hope I answered the question.
Yes, sir. Thank you.
We will go to the last question for the day. I could see students from 11A raising their hands. 11A, you have a question?
Good morning, sir. My name is Aditya. So, sir, I'm interested in learning about the current state of lunar exploration. So, sir, can you tell us about the ongoing or upcoming projects about like the professionals are working on, like about the NASA's Artemis program? And then, sir, I also have another question. So, are there any other countries or private companies that are doing cool stuff like this on the moon?
Yeah, indeed, Artemis is one of those big giants where we are trying to really go back to the moon, get a lot of data, and so that is something to look out for. But yes, there are also other space agencies who are actively involved in exploration of the moon. ISRO is one of them. There is also JAXA from Japan. There's also the CNES, or the European Space Agency, which is ESA. So we have a lot of activities ongoing for the moon. And so, all that data that's going to be collected, it is your generation essentially who is going to have a chance at using those data and exploring the moon and understanding a lot of improving our existing knowledge of the moon. So yeah, that's.
From 9E, we have one question. That will be the last
Morning.
question for the day.
Morning, sir. I'm Suyansh from grade 9E, and it's a simple question that I have. What are some of the various materials that are used in an orbiter?
You mean a spacecraft? What's the materials used in a
Yeah,
spacecraft?
some of the basic things which you use here.
Well, it really depends on the mission. It really depends on what's the spacecraft that you're trying to build. There's most of the things. Well, to be honest, I'm not an expert on building spacecrafts, right? I'm a scientist and not an engineer. So I haven't had a hands-on experience with building spacecrafts, but some of the things that we do see are like thermal protection is one of the major concerns, because in space you would expose your spacecraft to a lot of high temperatures. So there are materials specifically developed which are different layers of materials actually, which help protect the assets, which are spacecrafts or even ground assets. So the materials would really vary based on the purpose of your spacecraft.
Okay, I could see few hands going up, but due
So
to
I can take them. I can take the three,
Okay.
and probably we can end with the three.
Okay, Vaishnavi from 12A, could you please ask your question?
Hello, sir. This is Vaishnavi. I wanted to ask a question regarding your presentation. You basically displayed a graphic regarding the mass distribution on the lunar surface. And I wanted to know exactly why there's a higher lunar mass distribution on the far side of the moon, because of the higher amount of reds. But you also mentioned that there's a higher amount of volcanic activity over there. So wouldn't that essentially bring down the mass distribution? So my questions are, what are the relations between lunar volcanic activity and mass distribution, and why there seems to be more mass distribution on the far side?
Yeah. So the mass distribution, so for example, on the far side, we know the crust of the moon is thicker on the far side, and that really contributes to as overall you do see a excess mass, and there is also some of the major impact events that happen on the moon. The gigantic one is known as the South Pole Aitken Basin. It's about 1,200 kilometers diameter impact on the moon. So that's one of the major impacts that has happened. And so when a asteroid comes and impacts, you have all those material, it's called the ejecta, right? All those particles that are getting ejected or displaced from where it impacted to the surrounding areas. So one of the reasons is, that far side highlands, it could potentially be from those ejecta, but there is, our knowledge is not completely clear on why we have that. We think that it could be just, just old material from the highlands back when the moon was formed. And on the near side, you do see those impact structures and volcanism, right? And so that's mainly because, again, of this ejecta. There is, when a asteroid comes and hits the moon surface, the scale of that event is such that, think of it like a water droplet coming and hitting, a surface of water. You would get that bounce, right, once that droplet goes in. So that, and on those ripples on the side. And so really what we think is that freezing of that material, and as that impact happens and that rebound happens, right, the moon cools down in that over that time. And so that's why you see all those volcanism areas as well as impact structures and all those concentric rings on the moon's gravity field. Yeah, and great question. Yeah.
Thank you so much, sir. It was really enlightening.
Good morning, sir. My name is Vishnu. Sir, I wanted to know, as you said, you were a student here in Oman, and what were the challenges, or what did you go through from being a student here to being a space scientist now in?
Well, a lot of challenges. But in short, I think the takeaway is that, there will always be challenges, and what you want to do is endure them and, try to navigate them as you face them, and perseverance helps, because, much of the reward that you get from science is a very delayed gratification. So, it's not like clicking on that notification button when you get on Facebook or Instagram, right? It's a very delayed gratification, and that really helps cut through much of that time. And at one point, you're just going forward because of the love for science. And yeah, that's in short, but plenty more to share on that.
Yes, sir. Thank you.
I have one more question. My name is Hannah, and what are the prospects for commerce students in this particular field?
Yeah, that's a good question. So, so at NASA, it's not just scientists who work there, right? We have engineers, we have scientists, but we also have financial analysts. We have people who plan our proposal or budget for our proposals, and there's plenty of opportunities also in other domains to be working in maybe a space agency. So even if you're not doing science, you might actually be able to help scientists by trying to understand budgets, trying to account for them in terms of their allocations for research and equipments, and and salaries and FTEs, as they're called, which is just like an allocation of time based on the research, etc. So yeah, there's a lot that you can, maybe not particularly science, but you can work in a space agency even if you're not doing science. So
thank you, Dr.
Sir.
Vishnu. Over to you, Ashwati. I'm sorry. We are already, running short of time.
yes.
And I could see a lot of hands going up. I think you have ignited the spark in them.
Well, great. I'm really happy. And if there are more questions, what I can do is you can visit my website. There is a contact form. You're welcome to ask your questions, interact with me there. And the sign up, as it's open for you guys. And so I will respond to emails through that portal. So I'll take all other questions from there.
Okay. So thank you, Dr. Vishnu, once again. Over to you, Ashwati, ma'am.
Thank you, ma'am. So esteemed resource person, Dr. Vishnu Viswanathan, respected principal, Mr. P. Prabhakaran, amiable colleagues, and dear students, warm greetings. It is my privilege to extend our heartfelt gratitude to Dr. Viswanathan for his enlightening and thought-provoking session on planetary geodesy, the science of measuring and understanding the physical properties, shape, orientation, and gravitational field of planets, moon, and other celestial bodies. Dr. Viswanathan, your deep insights into the intricate world of lunar science have not only broadened our understanding, but also inspired us to think beyond our earthly confines. We are incredibly grateful for the time and effort you have invested in sharing your expertise with us today. The knowledge you have imparted will undoubtedly ignite curiosity and encourage further exploration in the field of planetary science among our students and educators alike. On behalf of everyone present, I extend our sincere thanks once again to you, Dr. Viswanathan, For this enriching experience, we look forward to future opportunities to learn from you and deepen our understanding of the cosmos. Thank you, sir.
Thank you. Thanks so much. Thanks everybody. And, really appreciate the invite from from Prabhakaran sir, the principal. And, thank you so much for organizing this. It was my pleasure to interact with all of you. And I look forward to seeing you on the other side.
Sure. Thank you very much. Thank you, students. Thank you, teachers, for joining. Thank you. Take care. Bye-bye.
Bye.